Namaskar, Sat Sri Akal. Today we will learn design of two-way slab. Okay, as I have already give you the introduction of slabs uh, in one-way slab part 1. Two-way slab is a slab in which it is in which it has 4 supports and the aspect ratio is less than equal to 2. Aspect ratio means the length in y direction to length in the ratio of length in y direction to length in x direction. Then two-way slab is of two types, uh, that is restrained slab and unrestrained slab. Then what is restrained slab and what is unrestrained slab, ये मैं आप लोग को बाद में बताऊंगी. पहले टू वे स्लैब हम इसको क्यों बोलते हैं टू वे स्लैब. इसको हम टू वे स्लैब इसलिए बोलते हैं क्योंकि ये जो उसकी लेंथ है in x direction and in y direction, in both direction deflection is and bending is critical. That's why this is called two-way slab. Then coming to next point, what is restrained slab and what is unrestrained slab. As the x and y direction length are nearly same, or in ly, that is ly by lx as less than 2, that is ly nearly equal to or that is ly nearly equal to or greater than lx. So these corners are critical during bending. Therefore we are providing torsion reinforcement in these corners so that the slab will not lift the corner. This type of slab are called restrained slabs. As per Indian standard, specifies two-way slab of providing fixity in case of restrained slab. Then unrestrained slab, the opposite one is unrestrained slab. Okay. Then coming to next point. As per we will design the two-way slab as per our code IS 456 Annex D. There are both method, that is for restrained slab and for unrestrained slab. The first thing is that the maximum bending moment. The bending moment is calculated as per unit width. That means for ly and for lx, both direction will calculated bending moment, but the moment will be critical in smaller span, that is lx direction. Therefore we will calculate the moment in x and y direction considering the span lx. Then there are as you are seeing that it mx is alpha x w into lx square and my is alpha y w into lx square. This alpha x and alpha y are the coefficients given in table number 23. Then in case of restrained slab, the slab is divided like this figure. the slab is divided into three part, that is middle strip and A strip. Middle strip is 3/4 of the span we are considering, and the A strip is 1/8 of span we are considering, that is both in LX direction and that is both in LY direction. Okay, now coming to next criteria. What is next criteria? Then deflection limit. In case of restrained slab, the span is limited to 3.5 meter, and the span by D ratio as well as span by D ratio with respect to the loading condition, loading class up to 3 km square, that is for simple supported slab 35 and for continuous slab 40 m, and these are restricted to these are restricted for mild steel bars, and for HYSD bar this value will be reduced by 20%, that is for simple supported slab, this will be 35 into 0.8 equal to 28, and for continuous slab 40 into 0.8, that is 32. Okay, if these values are exceeds, that is the span is greater than 3.5 meter and the load is greater than 3 km, then the slab is behaved as generally simple supported slabs, not like restrained slab. And for that condition, the span by D ratio as well as span by D ratio is same as simple supported slab, that is 26 for continuous slab, 20 for simple supported slab, and 7 for cantilever slab. But two-way slab, cantilever slab will not a two-way slab, only a one-way slab, simple supported slab is taken as two-way slab. Okay, then after deflection criteria, the two-way slab for designing two-way slab, we will assume its defective depth based on its span by D ratio from deflection criteria, because the slab is critical in the deflection in two-way slab, the deflection is critical in both LX and LY direction, but we will take the shutter span for deflection criteria, and from which we will calculate the effective depth from service stress and span by depth and span by D ratio. Okay, let us start with a problem. I think you can read the question. The question given as a drawing room of a residential building, given that a room size given, room size given 4.3 meter into 6.55 meter, that is LY direction, that is LX direction. Then we can take this aspect ratio LY by LX, what is coming less than 2 or not. Then we will assume its depth from its service stress criteria by assuming the percentage of steel as 0.4%, and the modification service stress at 0.58 fy. The modification factor from figure 4 for a S456, we can calculate it as 1.38. Then span, as span exceeds 3.5 meter and the load is and the load given is greater than 3 km, then we will consider it as a simple supported slab, for which span by D ratio is 20, and maximum permissible span by D ratio we can calculate from by multiplying with basic span by D ratio. 1 minute. We can calculate the base L by D max is equal to L by D into modification factor. L by D into modification factor. From that we will calculate depth. What will be effective depth? Then we will calculate overall depth. Okay. Then what is the next question given? Design this slab for that is given. It is supported on a 350 mm thick wall, supported on all four sides. The slabs is simply supported at edge with no provision to resist torsion at corners. No provision to, underlining it, no provision to resist torsion at corner. That means it will act as a unrestrained slab. Then for unrestrained slab, I have already tell you about that. The first we will calculate the mx and my, then we will proceed further, and the other things remain same as simple supported slabs. Okay, after calculation of overall depth, then we will calculate the effective length of span. As we know, effective length of span is Lx or Ly, which will be less. This will be the effective length of span. In Lx direction, as I have calculated, this is clear span plus effective depth. This is clear span for effective depth. This is 4.5 and this is Lx is 4.5 and Ly is 6.75. Then load calculation. Next step is load calculation. How we will calculate the load? By considering overall depth, we can calculate dead load, and we can assume floor finish if not given 1 km square for residential building, and live load as 2 km square for residential building. Then we can calculate the factor load. After calculating factor load, we can calculate the moments from Annex D of IS 456. Then we will check for depth. Is it visible? Yes. Then we will check for depth from the moment criterion. We know Q lim BD square is equal to maximum moment, as maximum moment is greater of mx or my. Then Q lim we can calculate at 0.138 FCK. From that, for material M20 grade and Fe415, this will be for M20 and Fe415, and Q lim will be 2.76. From that we can calculate D is equal to square root of mu by q lim into B. As we are considering per meter width, therefore B is equal to 1000. M we have already calculated, that is maximum 23.7 in 10 power 6, and q lim we are already calculated 2.76. Then we can calculate the depth, and the depth is coming that 92.7. depth is coming, what is depth coming? 92.7, but we are provided 160 mm. Therefore we can check in short direction and long direction is the depth is safe or not. In depth in short span is equal to 180 minus clear cover overall depth minus clear cover minus bar dimension by 2. 180 minus 15 minus 5 is equal to 160 mm. Then depth in long span, how we will calculate the depth in long span? Therefore a little consideration will understand you people. If this is the slab and one bar, and this is the cross section, actually this is the cross section of slab. If one bar is provided like this and the other bars like this, like this, like this, these bar are like this and these bar are like this. If this is one effective depth in LX direction and in LY direction, we can calculate the effective depth from this to this or not. That means one bar is like this and other bar is like this. That means one bar is like this and other bar is like this. If this is the LX directions overall depth, and this effective depth, this will be LY directions of effective depth. Then coming to flexural design. For flexural design we have to provide the reinforcement in short span and long span. For flexural design, the moment we can calculate mu by bd square, and pt we will calculate from the formula pt is equal to 50 into 1 minus 4 points root over of 1 minus 4.6 by fck into mu by bd square whole divided by fy by fck. From that we are calculating pt as 0.271, and ast we can provide pt bd by 100. ast we can provide pt bd by 100, and we can provide our ast as coming around 433.6. we can take it 434, and from that if we assume 10 mm bar dia, then the spacing we can calculate that from that area of one bar into 1000 divided by ast required. From that we can calculate the spacing, and the spacing is coming that about 180 mm, and generally we have how much spacing is we calculate, जनरली हम लोग उससे कम प्रोवाइड करते हैं टू सेफ अगेंस्ट क्रैकिंग क्राइटेरिया. Then we are providing 170 mm spacing. Then the AST requirement will be changed to 458 mm square. This will be in shorter span. Then we will check the minimum steel criteria in short span, that is AST min is 0.1 minute, that is AST min is equal to 0.12 times the cross sectional dimension, 0.12% of the cross sectional dimension. Then the minimum reinforcement coming about 216 mm square, and we can provide 50% bars bent off in shorter direction. Then calculating moment steel reinforcement in longer direction. For longer direction, mu y by bd, and then we will calculate pt in long span. जैसे हम प्रोवाइड किए थे शॉर्ट स्पान में, वैसे सेम ही प्रोवाइड करेंगे लॉन्ग स्पान में. बट सम एक्सेप्शन देयर. व्हाट इज दैट एक्सेप्शन? What is that exception? That exception is that the reinforcement requirement as compared to short span, the reinforcement requirement in long span is minimum. As here the long span not taking maximum moment, and the moment in long span coming around 252 mm square, sorry 198 mm square, and we will providing, if we will assume that 8 mm bar dia, then spacing is coming around 252 mm square. As the minimum, the AST in long span is less than minimum, then we will provide minimum steel in long span, so that the cracking criteria will not be satisfied, will not be failed. Then we are providing, by decreasing the spacing, we can increase our AST provided, that is we can provide 217 mm square in long span. Okay, already I have told it about the half of bar 10 bar can be bent off in short span, and the bars are bent off as per IS 456 Annex D at 0.1 L in each direction. Okay, then check for development length. For checking of development length, we have to calculate the, for checking of development length, we have to calculate this here, the moment. Why we are calculating moment? Because as in short span we are reduce the half of bar as bent off bar, half of bar as bent off bar, that's why moment will be somehow reduced. Therefore we are, as we have we all know to how to calculate the development length. LD is equal to 0.87 sigma y by 4 tau BD, and for M20 and AP4 and 5 this will be 47 hertz, and the development length formula should not, the development length should not less than, as per IS 456 formula, 1.3 M1 by V mu1 by V plus L0. In case of 2A slab, L0 is taken as 8 hertz or 10 hertz. I have taken 8 as. Actually design vary from person to person, that's why you can take 10 as. You may, आप लोग में भी ये भी प्रोवाइड कर सकते हो कि आप लोग बेंटो बार भी ना दे सकते हो, ऐसे कुछ दिक्कत नहीं है. ठीक है। बस इकोनॉमिक क्राइटेरिया के बेसिस पे हम लोग देते हैं क्या, बेंट ओवर। पहले हम कैलकुलेट किए हैं लॉन्ग स्पान में, क्या होगा डेवलपमेंट लेंथ। जनरली बिफोर कैलकुलेटिंग दैट आई मस्ट टेल यू दैट द डेवलपमेंट लेंथ और बॉन्ड इज क्रिटिकल इन लॉन्ग स्पैन, ये हमेशा याद रखना। दरअसल यहाँ से हम क्या चेक कर सकते हैं, ये हम दो तरीके से कैलकुलेट कर सकते हैं। आइदर हम उसको लेंथ में नोट कर सकते हैं, नहीं तो बार डायमीटर जो प्रोवाइड किए हैं उससे चेक कर सकते हैं। कैसे लेंथ में चेक करेंगे, हमारा डेवलपमेंट लेंथ 47 है, अगर 450 mm आ रहा है तो मिनिमम 450 mm से ज़्यादा हम डेवलपमेंट लेंथ दे सकते हैं। इन बार डायमीटर से कैसे चेक कर सकते हैं, अगर बार डायमीटर के हिसाब से ये मैक्सिमम 16 mm बार डायमीटर हम प्रोवाइड कर सकते हैं, तो हम लोग कितना बार डाया प्रोवाइड किए हैं, इससे हम चेक कर सकते हैं कि डेवलपमेंट लेंथ ज़्यादा है कि कम है। तो मैं जो चेक किया हूँ वो इसी हिसाब से चेक किया हूँ कि मैक्सिमम डायमीटर बार कितना होना चाहिए और हम कितना प्रोवाइड किए हैं। तो मैक्सिमम बार डायमीटर इन लॉन्ग स्पान होना चाहिए कितना, 15.01 mm, बट हम लोग प्रोवाइड किए हैं लॉन्ग स्पान में 8 mm बार डायमीटर। तो हम लोग मैक्सिमम से लेस प्रोवाइड कर रहे हैं तो सेफ जोन में जा रहे हैं, तो लॉन्ग स्पान में बॉन्ड सेव हो गया। पर इन शॉर्ट स्पान वी आर कैलकुलेटिंग again calculating the bond length, and this is coming that maximum diameter of bar should not exceed 16.90 mm, but we are providing 10 mm bar diameter, that's why we are safe in bond. Then check for shear. Shear is critical in long span, therefore we will take the shear force for long span. Why shear is critical in long span? Because of its less depth and less reinforcement we have provided, therefore we are checking shear stress in long span, that is BU 25.31 इन लॉन्ग स्पैन आया था हम लोग का। और हम जो ले रहे हैं B विड्थ, हम पर मीटर विड्थ में ले रहे हैं, इसलिए B इज इक्वल टू 1000 एंड D इज इक्वल टू 150 mm, एंड आवर टाउ भी, as we know tau v will be, the formula for tau v is equal to Bu by Bd, and it's coming around 0.169, and Pt we will calculate for long span, that is 100 AST by Bd, and it is coming around 0.145, and from table number 19 tau c we can calculate as 0.28. Then from table 18 we will calculate k tau c, and k tau c is greater than tau b, therefore we are safe in shear. Then deflection check, and deflection check, we know deflection is critical for short span only, and therefore we will check the span by d ratio for short span only. As the length is exceeds 3.5 meter, therefore we are taking this as simple supported slab, and for simple supported slab we know that span by d ratio is 20, then we can calculate the permissible span by d ratio, that is maximum span by d ratio, by multiplying the span by d ratio with modification factor, and this modification factor can be found out from figure 4 by considering PT, percentage of steel, and surface stress, in IS 456 this is given in like that, this is the surface stress direction, and here the modification factor, and here the PT, the corresponding PT and the surface stress will give the modification factor. Then from this we can check the deflection for this slab. So what is coming, the maximum surface stress coming, that is 228 Newton per mm square, and modification from that 1.54, and maximum span bed ratio coming there about around 1.54 into 28 10 30.8 mm, around 30.8 mm, and maximum span bed ratio 30.8 mm. Then we will calculate actual span bed ratio, that is actual span bed ratio is equal to the length along shutter span, that is the length along shutter span, that is 4.5 meter divided by depth 160 mm, the coming out 21.12, but maximum we can permissible up to 31.8, that is up to 32 mm, and we are safe in deflection. Then check for cracking. Cracking is a criteria which is safe, which you can make it safe by providing actual or required less than required spacing, and the maximum spacing permitted for short span, that is 3D or 300 mm, whichever is less, that is 300, the 3D means 3 times the effective depth, 3 into 160 mm 480 mm, or 300 mm, whichever is less, that is 300 mm, what spacing we have provided 160 mm, that is we are safe in cracking criteria in LX direction. For LY direction, that is for long span, this will be 3D or 300 mm again. Why we are taking both 3D and 300 mm? Because both the direction are primary direction for us. Nothing is a main steel and nothing is a distribution steel. For two-way slab, both are main steel. Then this is the detailing of the two-way slab we have designed. Okay, thank you. And if you are, the video is थोड़ा लॉन्ग हो गया है, वीडियो थोड़ा लॉन्ग हो गया है, बट for design purpose this video will teach you everything in a shortcut manner. If you require note, then comment me on inbox. I will send you my note. Okay, thank you. If you were thinking that the subject is little good, you can share and subscribe my note.